before moving on to more theory and more sort of heaviness, I wanted to take just a brief digression to do some examples of how to use the previous theorem. So the first example I want to present is a generalization of something we've seen before. But what I'd like to show is the previous theorem can be used to show that the rational numbers adjoint the nth root of 2 is a field. And moreover, it's a field that extends the rational numbers of degree n. The way that you go about showing this using the previous theorem is you just take the nth root of 2 and you show that it's the root of an irreducible polynomial. That demonstrates that it's an algebraic element, and then you know that what you've got is a field when you adjoin it to the rational numbers. So because the nth root of 2 is a root of x to the n minus 2, then an x to the n minus 2 can be shown to be an irreducible polynomial by Eisenstein. You know that when you take this element and you join it to the rational numbers, that you're getting a field. The reason that you know it has degree n is because of the irreducibility of x to the n minus 2 and the fact that that's a monic polynomial. Monic irreducible polynomial means it's the minimal polynomial, and we know that the degree of the minimal polynomial is the degree of the extension. The next example I just wanted to bring into play to show you that you can have repeated radical extensions that are not radical extensions. So I just built you a nice little tower of fields. Let's take f to be the rational numbers, and let's take k to be rationals adjoining the square root of 5. Again, you can prove very quickly that k is a field because the square root of 5 is an algebraic element. If you take beta to be the square root of the quantity 1 plus the square root of 5, then we can take the field k and just adjoin beta onto it, and this builds us a nice repeated radical extension of the rational numbers, f contained in k contained in e. The chain is, first we adjoin square root of 5, then we adjoin the square root of something in the middle field, and that's our little tower of fields that we need to build for an RRE. Then I've left for you as an exercise, just if you want to work with some specific examples. Let's suppose that omega is a root of the polynomial x to the 8th minus 1, but let's have it be a root of that polynomial that is not a smaller root. So for instance, it's not a root of the polynomial x to the n minus 1, where n is any number less than 8. So don't take 1, don't take negative 1, don't take I for that matter, but let's have omega be a root that shows up for the first time at degree 8. Then I'd like you as an exercise to determine the degree of the extension of q adjoined omega over the rational numbers. The last topic that I really want to cover in these videos, and we'll cover them more in videos to come, is the notion of a splitting field for a polynomial. So let's suppose that we start with a polynomial in a field. If f is a field and we look at f adjoined x, let's let f be a polynomial in that polynomial ring, and let's let E be a field containing the ground field f. We say that the polynomial f splits in the field E if f can be factored into linear factors in E adjoined x. We then go further to say that the field E is a splitting field for little f over capital F if, first of all, the polynomial splits in the larger field, and if it doesn't split in any smaller field. So if you have f containing k, which is strictly less than the field E, then f does not split over this smaller field k. Perhaps the easiest example of a splitting field is that the complex numbers are a splitting field for the polynomial x squared plus 1 over the field r. So x squared plus 1 is certainly a polynomial in r adjoined x. Inside C adjoined x, however, when we're allowed to use complex numbers in our polynomials, then we can factor this into linear factors. We can factor x squared plus 1 as x plus I times x minus I. So that shows that the polynomial f splits in the complex numbers. Additionally, x squared plus 1 is irreducible over the real numbers, so it does not factor inside r adjoined x. And because we're looking at a field extension of degree 2, and because we know that intermediate fields between the complex numbers and the real numbers would have to have degree dividing 2, and 2 is prime, we know that there aren't any intermediate subfields, and therefore there aren't any smaller fields over which this polynomial could possibly split. So that shows that we've got our splitting field for x squared plus 1. Now, the first thing is you define splitting fields. I gave you one particular example of where a splitting field exists, but it's better than that. It didn't matter that I chose the real numbers as my ground field or the complex numbers as my larger field. Whenever you start with a polynomial that's non-zero inside f adjoined x, where f is a field, as long as you've got a non-constant polynomial, so it makes sense to talk about this thing having roots and this thing splitting, then there does exist a splitting field for this polynomial. That's a theorem due to Artin, and that's a big theorem, and the proof of it is not particularly easy. I feel like I've hit you over the head with proofs of things so far, and I wanted to do one more big proof, so I'm going to choose not to do this proof. Gallian does do this proof in chapter 20 of his book, so I don't feel a huge amount of guilt in omitting this proof. Similarly, there's another theorem that we're going to want to know from this chapter, which is if you take a non-constant polynomial, or not the zero polynomial, in f adjoined x for f of fields, then there exists a field E containing the polynomial f, where E is a splitting field for f over f. Sorry, the theorem by Artin says that f has a root in some sort of field, and then the theorem that I want us to know is, in fact, it has a splitting field. Once you have Artin's theorem, the proof of this theorem that splitting fields exist is actually quite easy, and it's just a straightforward inductive argument. So again, I'm not going to prove it. It's a follow your nose proof. And I don't feel too much guilt because the proof, this proof is on page 357 of Gallian. But really what happens is you induct on the degree of f. So if f has degree 1, then f is its own splitting field. You know, the polynomial is already linear. And so you don't really have anything to prove. If you assume then that the polynomial has degree larger than 1, what you need to do is work inside of a field using Artin's theorem that contains a single root of that polynomial. Then you can factor out x minus the root, and the thing that's left over has smaller degree, and you can use your inductive hypothesis. And really, filling in the details of that argument is all you have to do the proof of the latter theorem here. So I'm not going to do it in detail. The proof that I would like to go through in detail, but I'm going to leave the video of that proof as optional, is the proof of the following two theorems. So they're kind of a handful to figure out, but drawing a little picture and working on pencil and paper can help you a lot with this notation. First is the one theorem, and then the corollary of this particular theorem is that splitting fields are in fact unique up to isomorphism, which is really cool. So let's see what this sort of building block theorem says. Let's suppose that theta is a map from a field f1 to a field f2. That's an isomorphism of fields. And let's start with a polynomial f1 in f1 adjoined x that's irreducible. And let's let f2 be its image under the extended map. When we take theta and we extend it to f1 adjoined x, we'll write the f2 for the image of f1 under theta. And then let's assume that E sub I contains the field f sub I, and that E sub I is actually f sub I adjoined alpha I, where alpha I is a root of f sub I. And again, I'm putting the i's there, but really I just needs to be a number that's 1 or 2. Then what we can do is we can extend the isomorphism theta to an isomorphism of the fields E1 and E2. And we can extend it in such a way that it agrees with theta on the ground fields. Right? So what is this isomorphism again? Phi maps E1 to E2, it agrees with theta on the ground field, and it carries the root alpha 1 of f1 to the root alpha 2 of f2 of the image. And that's exactly what this phi does. And this is a really useful theorem for us. This theorem by itself is useful, but it's useful because you can use an inductive argument for this corollary, which says that splitting fields are unique up to isomorphism. So that means take a polynomial f inside f1 of x that's non-constant, and take theta to be a field isomorphism from f1 to f2. If E1 is the splitting field for f over f1, and E2 is the splitting field for the image of f under theta over f2, then E1 and E2 are isomorphic. So if I start with one field and one polynomial, and I have an isomorphism of fields taking f to theta of f, then the splitting field for f is isomorphic as a field to the splitting field for theta of f. And if you apply this corollary in the case that f1 and f2 are the same field and theta is the identity map, then you get that splitting fields are unique up to isomorphism. I'm going to end this video with an example and a summary, and then I'm going to do a separate video where I go back and do the proof of those that theorem and the corollary of splitting fields are unique. Just this one example. Let's suppose that f is the rational numbers, which is really the motivating force for Galois, and let's let E1 be the rationals adjoining the fourth root of 2, something we've talked about already, knowing that that's a field. And let's let E2 be the rational numbers adjoin I times the fourth root of 2. It's very clear that E1 and E2 are not the same field. One of them is a subfield of the real numbers, and one of them is not. One of them truly has complex numbers in it, so they're definitely not the same field. However, according to the previous theorem, these two fields are isomorphic, E1 and E2. That's because both the fourth root of 2 and I times the fourth root of 2 are roots of the irreducible polynomial x to the fourth minus 2. Irreducible over the rationals, that is. And so, applying the previous theorem, there's a map from E1 to E2. It's going to be the identity map on the rational numbers, and it's going to carry the fourth root of 2 to I times the fourth root of 2. And that's the exact isomorphism between E1 and E2. So not only are these fields isomorphic, but they're isomorphic in this really specific way, which is cool, which is a very cool thing to know. Not only are these two things isomorphic, but I can tell you exactly how. You don't always have that in math. So a very cool example. And we'll see more like this. And now let me skip past these proofs that splitting fields are unique to go straight to our summary. So after studying these slides and taking a look a little bit at chapter 20 of your textbook, you should know and understand all the definitions that we have here. So as I stressed in the first video, you should know the definition of an algebraic element and a radical element. You should know the definition of an algebraic field extension and a radical field extension. And you should remember that there's a subtle difference between those two things. So they do not have the same type of definition as you would sort of want them to. And you should also understand the definition of a repeated radical field extension. The next thing is you should understand the connection between polynomials and fields that we discussed in these slides. So how is it that when we have an algebraic field extension, that this relates to polynomials? What is that relationship? And like I said, there's that lemma in the slides that I proved, which discusses this connection, but it's not even just enough to know the statements of the lemma, and it's really necessary to understand how we proved the connection between these two things, because those techniques are going to be used over and over again in these types of proofs. Third, I'd really like you to be familiar with the concept of a splitting field for a polynomial, and you should understand the extent of the uniqueness. So it's not that a splitting field is unique, period, but it's unique up to isomorphism, which is pretty cool. And last but not least, you should take a look at the computational examples in here, and you should be able to try to work with examples, with other computational examples that are similar. So, for example, I did a proof that Q adjoin the nth root of 2 happens to be a field. You should be able to prove something like Q adjoined, the fifth root of 9 is a field. That's too easy, but I can come up with something harder, and trust me, I will for your homework.